All right, I want to do another example where we can solve the problem using really multiple methods of chapter 10 and 11. And I'm really going to focus on methods of chapters 10 and 11. There is an energy way to get to the problem. The goal is to find the acceleration of an object rolling down this hill. And there's an energy method, and I really discussed it in class. And the reason why we can use the energy method is because the acceleration is constant. And I did something similar to that with the Edward problem I did. Let's see how many ways we can solve the problem. There's actually an easy way to solve this problem. And of course, there's a hard way to solve this problem. We're going to do it the hard way first. So suppose I have an object on a hill, and it's going to roll down the hill without slipping. And I've drawn here the free body diagram for all the forces acting on this object. Since the object is rolling, there's a force of static friction. There's also a normal force, and then there's also the weight of the object. I've also resolved the forces, and I've also defined the coordinate system along the plane. It's in red. It might be hard to see in the video. And here's my coordinate system. Okay? And I drew this earlier because we've drawn free body diagrams from an object on the hill. I think you're familiar with that. You should be familiar with these problems because we've been doing it for many weeks. The only difference here is the object is going to be rolling instead of sliding. This point of contact is stationary relative to the plane. Let me start by summing the forces along the hill. So we're going to call the direction along the hill the x direction. I'm going to say down the hill is positive. So we're going to call it the x direction. So let me sum the forces in the x direction. So down the hill I have g sine of theta. And up the hill I have the static frictional force. And that's going to be equal to ma of the center of mass of the disk. Remember, it's rolling down the hill without slipping. And the condition for rolling motion is that V center of mass is r omega, where r is the radius of the object, and A center of mass is r alpha. And the distance traveled is r delta theta, where delta theta is basically the angle through which this thing rolls. Let's sum the forces in the y direction. I have a normal force up and g cosine theta down, pretty easy. Now, we're going to be assuming that the object is rolling without slipping. We're going to be assuming that we're not at the point of slipping. Since we're not at the point of slipping, there is no relationship between S sub s and n. So I have, this is an unknown, this is an unknown, and this is an unknown. Well, this is a known, but I don't have the relationship between this and that. This doesn't add anything. It allows me to get the normal force, but that's it. In a sense, then, this one equation has really two unknowns. The second equation doesn't help. It doesn't have F sub s, and there's no connection between the normal force and F sub s because we're not at this point of slipping. So I need a third equation, and that third equation comes from summing the torques. I'm going to sum the torques about the center of mass of my object. Well, if I sum the torques about the center of mass of my object, the normal force goes through this point, mg goes through this point. So they don't produce a torque about this point. However, F sub s does produce a torque. And F sub s is going to produce a torque in this direction, in the clockwise direction. What's the lever arm for F sub s? Well, just this radius r. And so when I sum the external torques, I get my static frictional force times r equals I alpha. Now, it's true that the torque is clockwise. I could put a minus sign here, but if I'm solving for the magnitude of alpha, I will put a minus sign here. Of course, those minus signs will cancel, so I'm not going to put the minus signs here. This equation tells me that S of s is I times alpha over r, where I is the moment of inertia. This could be a disk, this could be a sphere. I'm just leaving it in general. Now, alpha is related to A center mass that way. So, alpha is going to be A center mass over r. So when I substitute that here, that's my force of static friction. That's all I can say, because remember, there's no relationship between these two, because we're not at the point of slipping. However, I can take this and substitute it up here, and I get, in the top equation, let me do it in blue, mg sine of theta minus I A center mass over r squared equals ma center mass. Let me move this to the other side of the equation. I'll factor out an A. And so this is going to give me the A so there's my acceleration. This is true whether I have a disc, a cylinder, a hoop. That's the acceleration. As long as we're below the angle where it slips. If we're at the angle where it slips, then yeah, this is going to be, this static frictional force will be mu times the normal force. If we're at the point where it slips, then this is going to be mu times mg cosine theta. And then we can put mu times mg cosine theta here. We can solve this for A and put it here. And we can find the angle where it slips. That's a homework problem, right? That's one of our homework problems. Of course, if I is 0, we have an object that's going to be sliding down the hill. And we get g sine theta. So this is one of the ways we can solve the problem. I will, in a second, show you another way. Okay, so I've erased the board. I want to show you another way to get to the answer, and it's going to be much faster this time. I have my drawing there. I want to calculate the acceleration of the system. It's rolling without slipping. I want to draw a bigger picture. Okay, what I'm going to do different this time, and I'm going to get the answer right away, is the following. We've learned in chapter 10 and 11 that you can calculate a torque about any point. You want to choose a convenient point to be able to solve your problem. So let's pick a point that's going to allow us to be able to solve the problem fairly easily. In fact, I want to choose a point of contact to sum my torques. And I can do that. I mean, it's convenient because, this point here doesn't slip relative to the inclined plane. It's as if this sphere, this it doesn't have to be a sphere, this object is rotating about this point. It does mean I have to use a parallel axis theorem for my moment of inertia because I've shifted my axis of rotation by r. Now, my frictional force is up the hill. It doesn't produce a torque about this point. The normal force passes through this point. It doesn't produce a torque about this point. But mg doesn't pass through this point. Mg passes through here. Mg is here. Here's mg. I'm summing the torques about this point. The vector r goes from the pivot point to the point of application of the force. This is the vector r. Now, let me draw some angles in. If I draw a perpendicular here, this angle is 90 minus theta. That angle here is 90 minus theta. This angle is theta. So the angle between r and mg is this angle theta. R times the sine of theta is going to be what? It's going to be the length of this. It's going to be this distance, which is the radius of this guy, times the sine of theta, which is basically this distance. This is going to be the lever arm. So, if I calculate my torque about this point, using my definition of torque, the force that we have here is mg. The length of this vector is really the radius of this object, and then the sine of the angle between these two vectors. So my torque is just mgr sine of theta. And of course, that's I alpha. But remember that it's rolling, so alpha is A center of mass over R. So let me replace that. But I is about this point, not about the center of mass. So I have to use the parallel axis theorem. I have shifted the axis of rotation by R. Let me use small m, sorry. And then mgr sine theta equals parentheses I center mass plus mr squared times A over R. Let me divide both sides by R, and let me rewrite this. Let me simplify this a little bit. I'm going to get so that the acceleration of the center mass is given by that expression. Now, when I did it the previous way, the I had in the equation was the I about the center of mass. I had to specify it here because I had to use the parallel axis there. Okay, so just be aware that in the previous method, the I was the I about the center of mass. So we get the same result, a lot less work. Okay, I've erased the board and I'm going to show you a third way to do this problem using the methods of chapter 11. So I'm going to use the fact that the sum of the external torques is equal to dl dt. I think this is a cool method to solve problems. Like I said, there's an example in your book, and you should take a look at it. When I was a student, I was never taught this method. I think it's kind of cool. So let's calculate, well, let's define our system first. Our system is just the object rolling around the hill. The external force acting on the system is gravity. Well, there's also the static frictional force. There's also the normal force. So there's three external forces. What I'm going to do is I'm going to sum the external torques, like I did in the previous example, about the point of contact. So let me do this again. I want to sum the external torques about the point of contact. So I have this vector r, whose length is the radius of this object. And then I have mg pointing down. We established that in the previous example that the angle between r and mg is the same as the angle of the hill. We know that torque is the magnitude of F times the magnitude of R times the sine of theta. Well, F is mg. This is, well, the magnitude of this vector is just the radius of this object. And so the sum of the external torques is mg r sine theta. Now, I want to use this expression to solve the problem. I need to calculate the angular momentum of this object about this point. Since I calculated the torque about this point, I got to calculate the angular momentum about this point. Well, the angular momentum L, since this is rolling, is I omega. But because I chose this as my pivot point, I have to calculate the I about this point, or I have to use a parallel axis theorem. And so the L here is going to be I of the center of mass plus, I keep using that capital letter, sorry, m r squared. That's my angular momentum of the system. And since it's rolling this way, you know it's clockwise. You also know that the torque is clockwise. Yeah, I should probably put a minus sign for the torque because it is clockwise. But the angular momentum is clockwise. When I take the derivative of the angular momentum, it's going to be clockwise. The minus signs are going to cancel. So I'm not going to be concerned with the minus signs. If I had two terms here with opposite torques or opposite angular momentum, I would start putting in the signs. All right, so using the fact that L is I omega and that we've shifted our axis of rotation by R, I had to use a parallel axis theorem. This is L. Okay, let's write this down again. L is I center mass plus mr squared times omega. Let's take dl dt. dl dt is going to give me, well, these are constants. The only thing I can take the derivative of is omega. The derivative of omega with respect to time is alpha. But alpha is a center mass over r because it's rolling. So let's put this here. Let's divide both sides by r. Okay, I just divided both sides by r. Now let's solve for a center mass. Oh wait, before I do that, let me simplify this. I'm putting it in the familiar form as I have had in all the problems I have done in the videos. And so a center mass again, you see I get the same answer using a different technique. And so if you put in the moment of inertia of the object, the masses will cancel. That's one thing I haven't pointed out before. This moment of inertia is going to have the mass of the object, all the ends will cancel. You'll have a g sine of theta times some constant for the acceleration. Okay, I have erased the board again, and I know I'm beating this problem to death, but I'm going to solve this problem one more way using this expression. The only difference is I'm going to do in this case as compared to the previous one is I'm going to choose a different point in which I'm going to sum the torques and the angular momentum. So I'm going to sum the torques about this point. I'm going to use this method. All right, my system is just this object. I'm going to sum the torques and angular momenta about this point, and I'm going to come up with the same answer again. So let's sum the torques about this point. Now there's three forces here. There's a frictional force, there's the weight of the object, and then there's the normal force. And I showed you earlier that since the normal force and the g pass through this point, they're not going to produce a torque. The only thing that's going to produce a torque is the static frictional force. So if I sum the external forces, and really well, anyway, if I sum the external forces, I'm just going to get the static frictional force times the radius of the object. And I want to set it equal to dl dt. And probably don't need the arrow over there over these because I'm just going to define clockwise as negative, counterclockwise as positive. Okay, and this rotation is clockwise. And so I'm going to have a negative term here, and the angular momentum will be clockwise also. The minus signs will cancel. So I might as well just say, let's define clockwise as positive and counterclockwise is negative. It's just a convention, and I can do that. Okay, I can define clockwise as positive and counterclockwise as negative. It doesn't matter, as long as I can differentiate between the two. All right, so I have this. I need my expression for the angular momentum. What is the angular momentum of the system about its center of mass? Well, that's going to be easy. L is going to be I, center of mass, omega. That's it. What's d L dt? It's going to be I alpha. Okay, so d L dt is going to be I alpha. I'm going to set these two equal to each other. And of course, alpha is A over R. The problem is the static frictional force. Now, let's take a look at the free body diagram. I need to figure out how to eliminate this. I can eliminate it by summing the forces in the x direction. If I sum the forces in the x direction, I did this in the first version of this problem, if I say down the hill is positive, I have mg sine of theta minus f sub s equals ma. If I solve this for f sub s, I'm going to get mg sine of theta minus ma is f sub s. I'm going to take this and substitute it up here. And this I is the moment of inertia about the center of mass, so I guess I should label it about the center of mass. I'm going to divide both sides. Oops, that's not f sub s, it's ma. I'm going to divide both sides by r. Then I'm going to move my ma to the other side. And you can see I'm going to get the same expression again. I've solved this problem 4 different ways. I got the same answer. So one of the things I like about doing problems like this is that you get to see all the physics in this problem. You get to see the connections between forces and torques and the momentum. It is really good to be able to solve problems different ways. So if you can try to solve problems using different methods, that's great. I think you understand the material better. So that's something you should try to do.